Hey team, today we're going over polynomial functions, and we have multiple topics in this one, so it'll be a polynomial review. Let's go ahead and begin. So here, let's zoom into our first problem right here. Number 1, find the zeros by factoring, then state the multiplicity for any repeated zeros. Well, the first thing we need to do is whenever we're factoring, we have to first look for a GCF, or any greatest common factor, and then we notice that each term has an x. So we'll go ahead and factor that x out. And so, we'd have x, and then remaining would be x squared minus 8x plus 15 in parentheses. And now we can look, hey, what multiplies to 15 and adds up to negative 8? And so x would stay in the front. We'd have two sets of parentheses if we were to factor this. And let's see, x times x would be our x squared. And 15, let's see, so I'm thinking 3 and 5, because negative 3 and a negative 5 would multiply to be a positive 15, and they would add up to be negative 8. So, though, that is basically it. And to find the zeros, we'd have each thing here, x would equal 0, x minus 3 would equal 0, and x minus 5 would equal 0. Solve each of these for x. Well, this one's already done. Add 3 to both sides, so x equals 3, and here you add 5 to both sides, so x would equal 5. And those are your zeros. There is no repeated solution, so every term, every answer is a multiplicity of 1, so we don't need to write that next piece down because everything is a multiplicity of 1. We don't have an extra 5 anywhere, or an extra 3, or an extra 0. On to the next. Alright, so number 2, here we have write each polynomial in standard form, classified by degree and the number of terms. Okay, so a couple things going on. Well, the first thing is, let's get this in standard form. And so we have a jumbled polynomial function here. Let's see, so standard form means we have to have the biggest power written first, and then it goes down in sequential order from there. And so the first one I see would be negative 3, x to the 6. And then after that, looks like we have x to the 3rd. And if you see like terms, definitely combine them. So 4x cubed minus 3x cubed would just be a positive 1x cubed. And then it looks like we also have some common terms like right here, so 2x plus an x, well that would be a positive 3x. Alright, so we have it in standard form, and that's good to go. So now classified by degree and number of terms. Okay, well the biggest degree is 6, and there is an official name for it, but at this point usually the general rule of thumb is after 5, what ones are bigger than 5, you can just say, hey, it's a polynomial of 6 degrees. And with 1, 2, and 3 terms, it'd be a trinomial. So we're going to say this is a trinomial of 6 degrees. Alright, here we have number 3 and number 4. We have describe the end behavior and the number of possible turning points of the graph of the polynomial. Okay, so number 3, the only thing we have to really look for is, in the end behavior is the first term, the leading coefficient and the highest degree. So it looks like here we have the leading coefficient is a negative number and the highest degree is an even. And so, with an even degree and a negative leading coefficient, that means we will have an end behavior of down and down. And that's literally all you need to write. And so, basically in the graph, you could have a couple squigglies, but at the end of the day, hey, on the left side, it's falling down, and on the right side, it is falling down. And there are a couple different ways to write this. However, one of the most simple ways is just saying, hey, it's down on the left, down on the right. And the number of turning points, well, you just take your highest degree and subtract 1. So it'd be a maximum possible number of 3 turning points. And with a little illustration here, you have 1 turn, 2 turns, and then a 3rd turn. And it would have down and down for the directions. And that's just a sketch, not an accurate graph of what that would be. Number 4, let's see, we have a positive leading coefficient and an odd power. Okay, so let's see, if I'm thinking positive, it starts down and the bottom left goes up to the right, so this would be down and up for our end behavior. And let's see, with a power of 5, that means we'd have 4 turns possible, so a maximum of 4 turns for this graph. And again, if you were to sketch it, you could start down, 1, 2, 3, maybe something like this. You'd have 1, 2, 3, 4 turns in your graph. Alright, let's go on to the next. So here we have it, number 5. Determine whether x plus 7 is a factor of the function by dividing. Okay, So we have 4x cubed plus 38x squared plus 60x minus 70 divided by x plus 7. Okay, well, we could do a long division and polynomial long division. However, we have this thing happening. This is a power of 1 and a leading coefficient of 1. Whenever that is the case, I'm going to use synthetic division. So here's how I set it up. And a little differently than other videos, but I draw an upside down division symbol. And then you take the opposite of this one, so the 0, if you had a 0 here, you'd solve it, and so it'd be -7, so we'd place a -7 on the outside. And here, we very important, must check that everything is in order, so we have an x to the 3, an x to the 2nd, an x to the 1st, and then x to the 0 here, even though it's not written, it'd be x to the 0. All of it is in order, all of it is written, it doesn't skip a number or anything like that, and so we just write these numbers. If it did skip a number, you just fill in a 0 in this list. So let's see, so 4 would go here, a positive 38, a positive 60, and a negative 70. Yes, write down the signs with it. Okay, so the process of synthetic division is, we start by dropping down the first number, and then multiply the outside. So -7 times 4 is 28, or -28. And then you'd write that right here. And then add or subtract these. Looks like this time we have to subtract. So what's remaining? Well, 10. And then -7 times a 10. Well, write it in the next diagonal spot to the above, and we'd have -70. And let's see, okay, then remaining we have -10, -7 times a -10, we have a positive 70, -70 plus 70 is 0, and hey, we have no remainder right here, right? So we have 0, which means, yes, x plus 7 is a factor. And there you go. Okay. On to the next, number 6. So in this one, they're saying find the zeros of the function, then state the multiplicity for any repeated zeros. Okay, well, looks like they're kind of friendly to us. They already factored the original polynomial. So we're left with these factors, x minus 5, x minus 7 squared, and x plus 6. So let's go ahead and finish the job off. And we have x minus 5 equals 0. We have x minus 7. And we have two of them, right? So x minus 7, both of these would equal 0. And then we have x plus 6 equals 0. Okay, so add 5 to both sides, x equals 5. Add 7 to both sides, x equals 7. Add 7 to both sides, x equals 7. Minus 6 to both sides, x equals a -6. Okay, so your zeros are x equals 5. And then you don't have to repeat it. And so the multiplicity, here's what they mean by that. We'd have 7 with a multiplicity of 2, so you could just say 7 multiplicity of 2, something like that. And then here, x, of course, would still equal 6. So anything like that, that's an acceptable format, that would work. It just states that, hey, you have 2 number 7s, not just 1 number 7 as a solution. Alright, on to number 7. Write a polynomial in standard form with given zeros. Okay, so this one, they solved a polynomial. They got these answers as a 0. And this time we have to almost work backwards and find the original polynomial function. And so to do that, we'd have set x equal to all of these numbers. So x equals 0, x equals 2, and x equals -5. So here, well, x equals 0, well, hey, it's just going to be x, right? Because you subtract a 0 on both sides, you don't need to write x minus 0, x plus 0, it's just going to be x. And here, subtract 2 to both sides, so if I wrote it down, we'd have then x minus 2. And then this term, we'd add a 5 to both sides, so it gets closer to x. So add 5 to both sides. Then it's all of a sudden 0 on the right, just like here, 2 minus 2 is 0. And we'd have x plus 5. So here's our polynomial right now. We have x times x minus 2 times x plus 5. Now we go ahead and multiply, so we can distribute, or FOIL, whichever you prefer to call it. So x times x is x squared. X times 5, well hey, that's just going to be positive 5x. Then -2 times x is -2x, and -2 times a 5, well hey, we're at -10. Okay, combine your like terms. So we have x squared plus 3x minus 10. And then the final step, multiply this x through to all three terms, so we end up with x cubed plus 3x squared minus 10x as your original polynomial. There we go. And it's in standard form, the biggest power is in front, and it goes down in order from there. On to the next, to number 8, here we go. Okay, so write a polynomial function of least degree with integral coefficients that has given zeros. Okay, interesting. So here, similar to the last problem we just did, but now we have an imaginary. And so they didn't give us all of the zeros, because they gave us 4, an integer, they gave us negative 2i, but whenever you have a square root or imaginary numbers, the additional 0 would be a positive 2i, right? Just because if they gave me, let's look, because if I had the square root of 25, right, the answer would be a plus or minus 5. Yeah, and if they gave me a square root of negative 25, the answer would be, let's see, we'd say a negative, a plus, or a minus 5i. And so if they gave me just one of those, well, if they gave me the negative one, I also know the positive one is part of that solution. So they didn't write that down for us, so it's up to us to go, hey, an additional 0 is actually a positive 2i. Okay, so let's get rid of this real quick. That's just illustrative to that purpose of getting the additional 0. And so we have x equals 4, x equals a negative 2i, and x equals a positive 2i. So now we subtract 4 to both sides, so we have x minus 4 in parentheses. We add 2i to both sides, so we have x plus 2i. And then here, subtract 2i to both sides, so we have x minus 2i. Now at this point, you have an option. You can multiply any binomial with any binomial. However, it will save you a little writing if you multiply the ones that look very similar to start. So that's what I'm going to do. I'm going to multiply these two first. So x times x, well, hey, that's going to be x squared. And then x times negative 2i, well, that's just going to be negative 2ix. Kind of weird, but all the terms are just sitting side by side, multiplying each other. Then 2ix again, oh, that's a positive 2ix. And then, right here, 2i times a negative 2i, we would have negative 4, and I times I becomes I squared. Okay, at this point, let's combine our like terms, so negative 2ix and a positive 2ix will cancel out, they would be 0. And so that leaves us with x squared minus 4i squared. And this can be broken down a little more, because I squared, if you remember your i's and your imaginary numbers, I equals the square root of negative 1. So, I squared, well, if you were to square that, right, well, squares and square roots cancel each other. So I squared would just be the number negative 1. So this actually changes a little more, because negative 4 times a negative 1 is a positive 4. So it's x squared plus 4 right here. So, we have this binomial multiplied by this one. It's been sitting in front for a while waiting for its turn, and so we have an x minus 4. Okay, so let me rewrite that so we have some room to multiply. So we have x minus 4, and we have x squared plus 4. So let's multiply these together to get our final answer and our final polynomial function. So x times x squared would be x cubed. X times 4, well, that'd just be positive 4x. Negative 4 times x squared is negative 4x squared. And negative 4 times a positive 4 is negative 16, okay? It doesn't look like we have any terms to combine. However, let's get in standard form. So it would be x cubed minus 4x squared plus 4x minus 16. And that is our polynomial function for this problem. On to the next, number 9. Here we go. So use the rational root test to find and list all of the possible roots. Very interesting, okay. So basically, to shortcut this, the last term here we'd call like term p, this very first leading coefficient we'd call q, and we have this lovely thing, and we have to mind our p's and our q's, okay, so p's and q's. So the p's would be all of the factors of this negative 12, or this 12, and it's actually, the sign won't matter in a moment, and the q's would be all of the factors of this number 3. So let's make that list. So, what multiplies to 12? Well, a 1... what factors do we have of 12? So what divides 12, really? And so 1 divides a 12, so does a 2, so does a 3, so does a 4, so does a 6, and so does a 12. All of those are factors of 12. So those are our p's. And then what divides a 3? Well, 1 does, and so does a 3. So if we're going to generate a list, we have to divide all of these numbers on top, and by all of these numbers underneath in the denominator. So, let's start with a 1 as a denominator, because that's pretty easy. And so all of these will be plus or minus. So we'd have 1 divided by 1. Well, hey, that's just plus or minus 1. 2 divided by 1, plus or minus 2. 3 divided by 1 is plus or minus 3. 4 divided by 1, we have plus or minus 4. And then 6 divided by 1 is a plus or minus 6. And 12 divided by 1 is a plus or minus 12. On to the next. So that one's done. Now we have 1 divided by 3. Which is, hey, plus or minus 1/3. 2 divided by 3 would be plus or minus 2/3. 3 divided by 3 is a 1. We already have that in the list, so we don't need to write it twice. 4 divided by 3, that's a new one, so plus or minus 4/3. 6 divided by 3 is a 2. We already have that on the list. And 12 divided by 3 is a 4. We already have that on the list. So there you have it. If this were to have any rational roots, it would come from this list. It would have to be a positive 1 or a negative 1, a positive 2 or a negative 2, or any of these other numbers to try if this were to have any rational roots at all. And that is how you find it. Okay, and so if we were to continue this problem, if they said factor and you wanted to divide it, well, you wouldn't just test any number, you would test numbers from this list. Okay, on to the next, number 10. So here we have a few different things. Find all zeros of each polynomial. Okay, well, it looks like these ones we just have to factor, so let's check out number 10. Again, it looks like, hey, we have an x in every term. So the first thing is that's the GCF, take that x out. So that leaves you x squared plus 2x minus 15. And yeah, it equals 0. Okay, so what multiplies to negative 15 and adds up to a 2? Well, we still have the x in front, don't forget about that. And then let's get our format, and yeah, it still equals a 0. And so negative 15, I'm thinking 3 and 5 again, with a 5 being positive. So the 5 would be positive, and negative 3, that adds up to a positive 2, multiplies to negative 15. There you have it. And find all the zeros, so either x equals 0, x plus 5 equals 0, or x minus 3 equals 0. Okay, and whenever items are multiplying and they equal 0, well, that means one of these things has to equal 0. If you're not sure, well, hey, set them all up. So x equals 0, that one's finished. Minus 5 on both sides, x equals a negative 5. And here we have, I don't want a triangle, let's make that an x with an underline, there we go. And then here, add 3 to both sides, x would equal 3, and those would be, not a triangle again, those would be your zeros for this problem right there. 0, negative 5, or positive 3. Alright, on this one, a little different, but hey, same concept. We have x to the 4th plus 4x squared minus 21. So here, if we're going to factor this at all, you could replace this with an n and have, say, n equals x squared, and then plug it back in. Or you could just say, well, you know what, x squared times x squared becomes x to the 4th. And then, let's see what multiplies to negative 21 and adds up to a positive 4. So I'm thinking 7 and 3, with a 7 being positive. Because if you were to multiply this back, well, you'd have x to the 4th, and then x squared minus 3 would be negative 3x squared, then plus 7x squared, that would give you that 4x squared in the middle, and then 7 times a negative 3 would be negative 21. So if you were to check it, you would just distribute, you would FOIL, and see if you get what you started with. And now let's continue. So x squared plus 7 equals 0, and x squared minus 3 equals 0. Okay. So finding the zeros of this, we'd subtract 7 to both sides, so x squared equals negative 7. Over here, you'd add 3 to both sides, so x squared would equal 3. And here, you have to take the square root to cancel out the squares, so square root both sides. And so on this one, it'd be x equals plus or minus I squared of 7. And yeah, you could get the decimal, but we have that negative square root, so you'd have an imaginary right here. In this one, a little more straightforward. When you square root both sides, well, it'd just be x equals plus or minus the square root of 3. And yeah, you could get the decimal form. However, in simplest radical form, this, you can leave it just as is, how that looks there. Alright, there is one more find all zeros of polynomial. Let's look at number 12 right over here to the side. So here we have 3x cubed minus 7x squared minus 18x minus 8 equals 0, and they gave us one of the factors. They said x minus 4 is a factor. Well, that's really helpful, because if it's a factor, that means it's a 0, so they basically gave us one of the answers. And that's also a tip, we don't need to make our rational root list. Let's just go ahead and divide this function by x minus 4. So, I'm going to draw my upside down division for synthetic division. The opposite of negative 4 would be a positive 4, so that'd be a 0. And let's check our list, so we have all of our powers in order, it's not skipping any. So we'd have 3, minus 7, minus 18, and a minus 8, all right here. So, first step in synthetic division, you drop the 3. 4 times 3 would become 12. So write it up here in the top diagonal. Negative 7 plus 12 would become 5. 4 times 5 is 20. And then negative 18 plus 20 is 2. And then 4 times 2 becomes an 8. And negative 8 plus 8 is 0. Okay. Makes sense, we had no remainder. So hey, it is a factor, they weren't lying to us. So let's rewrite our equation right now. So as of right now we have x minus 4. in front, multiplied by 3x squared plus 5x plus 2, and then the remainder is 0, so we don't have to write 0 over x minus 4. Nope. It's just like that. So, and it makes sense if we were to multiply this back in, we'd get our original problem. So now, let's look. Can we factor this right trinomial? So, let's give it a shot. Otherwise, it's a quadratic. So right now, we have one option. It's going to be a 3x and an x if we have integers here. And so, because 3x times x would be 3x squared. And so, the only things that can multiply up to a 2 is a 1 and a 2 for integers. So, let's see. I'm going to try the 2 to be right here, and the 1 to be right here. Because when I check this, 3x times x would be 3x squared. 3x times a 1 would be 3x. And then 2x here, let's just write it down, let's check. So we'd have 3x squared for the first terms. Then we'd have 3x times 1 is just 3x. 2x times, well, 2 times x is 2x. And then 2 times 1 is 2. Well, 3x plus 2x is 5x right in the middle. Hey, we got the middle term to match. We got the last term to match. That would be how we factor it. So let me erase that checking work so we can finish off the problem. And when in doubt, you can always check your problem, see how you're doing, see if it's the right step. No problem there. So here we have x minus 4 equals 0, 3x plus 2 equals 0, and x plus 1 equals 0. Well, here this one is pretty easy. Subtract 1 on both sides, equals negative 1. The one on the left over here is pretty easy. Add 4 to both sides, x equals to 4. This one's actually a two-step equation. You have to subtract 2 and then divide the 3. So x here would actually equal negative 2/3 for your last 0. Alright, on to the next, number 13. So here, we have to expand the binomial. Okay, so we have x plus 3 to the 5th power. And to do this, we could multiply x plus 3 together 5 times and combine our like terms over and over and over again. The shortcut we talked about is we have Pascal's triangles. So here's term 1, term 2, term 3, term 4, and term 5. So we generate this triangle by adding the last 2 items above it. So like 3 plus 1 is 4, 3 plus 3 is a 6, 1 plus 3 is a 4, and of course the edge would be 1. And that's how we get these numbers to be generated in Pascal's triangle. So here we have Pascal's triangle. Let's get our number of terms. So this would be term 0, term 1, term 2, term 3, term 4, and we want the term that matches our power, so let's generate one more. So we'd have 1, 5, 10, 10, 5, and 1. This would be term 5 right here. So these are the numbers that we're going to pull. You could make this triangle as long as you wanted, forever and ever. This is what we're looking at right here. So we'd have this number right here. We'd have 1, and then you're going to write your 2 terms here, x and 3. So 1, x, 3. And we do have some powers. I'll write those in a moment. The next we'd have plus 5x and 3, plus 10x and 3, plus 10x and 3, plus 5x and 3, plus 1x and 3. Okay. So, every single term has to add up to a power of 5. So this first one, it'll be x to the 5th. Well, and if that has all the powers, this one's going to be 0. So here, we have x to the 5th, then we have x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and x to the 0. 3 is going to go the opposite way. So we have 0, 3 to the 0, 3 to the 1st, 3 to the 2nd, 3 to the 3rd, 3 to the 4th, and 3 to the 5th. Notice each time these powers, 5 plus 0 is 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, 1 plus 4 is 5, 0 plus 5 is 5. They add up to that biggest power every single time in all of these terms. Now we just have one more step to go. Let's simplify this. So, 3 to the 0 is going to be 1, and 1 times 1 would be 1. So our first term would just be x to the 5th. 3 times 1 is 3. Or 3, excuse me, that is a common mistake. 3 to the first power still would be 3. And then 3 times 5 would be 15. So we have 15x to the 4th. 3 squared would be 9. 10 times 9 would be 90, giving us 90x cubed. 3 cubed would be 27. And then 27 times 10 would be 270x squared. 3 to the 4th power would be 81, and then 81 times 5, we have 405 x to the 1st, and then 3 to the 5th power times 1, we'd have 243, and x to the 0 would be 1, so that would be the number. Alright, moving on to the last one for this review, number 14, we have a lovely graph here. And they're friendly to us. They already factored our polynomial for us, so let's just finish the job. And so we'd have here x would equal a 0. So let's find the zeros, that's what we need to do. And then x minus 2 would equal a 0, and here x plus 3 would equal a 0. And so that stays as x equals 0, right? And here add 2 to both sides, so x equals 2. Minus 3 to both sides, x equals negative 3. Okay, these are the zeros. So on your graph, you're going to place a dot on your x-axis because that's where it's 0. So you have a 0 at 0. You have one here right at positive 2, and the other dot would be here at negative 3. So that's where we get those zeros, because hey, that's when you're on the x-axis, your x-axis is 0. That's why we call them zeros or solutions, anything like that. Now, let's see. We have the biggest term. If we were to get the original function, the polynomial function, you'd at least multiply 3 x's, which means the biggest power would be x cubed. And it looks like there's not a negative sign here, it's a positive, so it'd be a positive x cubed. Okay, so we have a positive leading coefficient, and the biggest power would be 3 in this case, which means you'll have an end behavior of starting down on the left and up on the right. So our end behavior would be down and up. That's really important, and if you're just sketching the graph, you're not asking for an exact graph, well, that's really helpful, because that means we just have down, and then we'd loop around to get these dots, and it'd be something like that. Now again, right now we're not focused on the accuracy of these loops, or how deep they go, or how low this one would go. We are asked to just sketch this graph, and so sketching the graph, you get the end behavior, you get your y-intercept, call it good. Hey, we sketched the graph. Alright, there you have it. We have reviewed polynomial functions, going over 14 problems, various things, factoring, finding P's and Q's, doing synthetic division. I hope this helps you. Good luck on your practice.